Okay, well, thank you very much to Tom and the other organizers. I'm excited to be here and looking forward to hearing about all the interesting things people are doing in this area. So I'm going to report on a paper we just put out with Batra, DeLuca, Taroba, and Yang, which is also related to earlier work with Edward, Ronak, and others. And the nice thing is it's not just related to what's going on in our group. So in the past, it's been the case that people working on de Sitter spacetime have kind of been in their own world, like their own observer patch, and not exactly connecting to the other ones. But these days, it's been great because things are coming together in certain ways. Of course, there's a lot of interesting subtleties with the subject, so I'm going to try to explain this work and put it in a bigger context. Okay, so I think the motivation is likely clear, but let me do it for completeness. The cosmological constant permeates our observable universe. It's most of what there is. We're just kind of an afterthought. It's also from the bottom up, the most relevant term in the action. And from the top down, it's what string theory, this is a string theory workshop and conference, it's generically what string theory does almost 100% of the time. And I can say that so easily simply because, say you compactify string theory starting from some higher dimensional limit of it, typically that compactification will be curved, and typically it'll be negatively curved, and that gives positive potential energy from the start. And there are other ingredients that tend to give de Sitter minima. If I get there, I'll explain the latest example of that given recently by DeLuca et al. Okay, so what we want to do in the quantum gravity setting, of course, there are cosmological observables that are literally observed. But in quantum gravity research, we would like to formulate quantum gravity in the presence of the positive cosmological constant to understand what kind of observables there are and what kind of calculables there are. So one of the targets of the subject is the famous Gibbons-Hawking entropy. So somewhat like black holes, but a little bit more subtly. There was an old argument that was refined recently that there is indeed an entropy associated with the observer patch in de Sitter space-time. I'm going to immediately retreat to 3 dimensions, and here I'm quoting the corrected expression for the Gibbons-Hawking entropy in 3 dimensions, with the correction coming from this paper of Ininos et al., where, like what Ashok Sen had done for black holes, for BTZ black holes, you get a correction which specifically is this -3 log of the Gibbons-Hawking entropy. So all this has long suggested that there is a finite Hilbert space that should capture the physics of the observer patch. And a kind of incomplete list of people who have talked about that is on the slide. Okay. Now, the next thing I'm going to do is recognize that gravity is geometry and topology. And, you know, topology is much more general than, say, the global de Sitter space-time. In particular, if time-like boundaries are allowed, and there's a very active research program going on to understand that, especially in 4 dimensions, but if they're allowed at all, they are quite generic. The case with global de Sitter is just kind of an exception, and most of the time with such things, they would be, you know, the rule, not the exception. And in particular, from the bottom up, you can easily consider the case where you do have some boundary with some good boundary value problem, ideally a good initial boundary value problem, and maybe stability properties, maybe not, depending on the physics. So as you can imagine, having a time-like boundary, which I'm arguing is generic, is also extremely helpful for holography. For the same reason it is in ADS, you can anchor some quantities which are frozen at the boundary, depending on your exact choice of boundary conditions. Some stuff is frozen at the boundary. The conjugate stuff is what fluctuates. It makes holography much easier to make sense of with positive cosmological constant, in making it much more like it is the familiar case with the negative cosmological constant. There are, you know, interesting subtleties with boundary conditions, which we will not really confront in this 3-dimensional example, but we have ambitions to go beyond that, so we are paying attention to that. It's also interesting, and again, this being a string theory workshop, these boundaries are, short scale features, so it's a UV sensitive question. And some of the issues people raise with boundaries have to do with really short scale modes, so that's a UV issue. And string theory could have a lot to say about it. In fact, there's some, I think Victor might talk about stuff related to this in a certain way. I had some comments in a paper. And in string theory, Amadane, Kahn, and Wall have some results, or some results in progress on formulating that in string theory. And I saw Aaron last week in Chicago, and he was optimistic about this. Okay, so the point of this talk will be to develop what we like to think of as an algorithmic, and I'll explain this, deformation of ADS-CFT, preserving the existence of the time-like boundary in the setup in such a way that we can define the time-like bounded patches of de Sitter space as certain semi-classical states in a theory whose spectrum we can calculate, and for which, say, the bounded cosmic horizon patch corresponds to a band of energies at the top of the spectrum. The bounded pole patch corresponds to the lowest state, has very little entropy, and we'll have for very natural reasons, a finite spectrum that indeed captures the entropy of the cosmic horizon patch, while at the same time this theory has the correct emergent de Sitter geometry. Okay. Now, I can't help myself. I do want to think toward 4 dimensions, and could there even be observational constraints if these things make sense, but I won't, so I'll mention that later, but not do much with that yet. Okay, so just to get everybody on the same page, I know some of the people here have thought about this going way back. I know Don and George and others and Mukund have been early adopters or early detractors, I'm not sure which, of the possibility. And I'm kind of late to the party, but I'm a real enthusiast now. So, but not everybody has thought about this. And I should say I myself am kind of late to this. I used to view de Sitter as inexorably, coupled to gravity, no way of getting out of it. But this is a way out of it. So with a time-like boundary, the first thing to say is that in terms of this question of what observables there are, one set of observables, which I already mentioned, which is really important, is that the energy spectrum is an observable. So just to make that intuitive, say if you go back to electrodynamics, if you have a closed space, then Gauss's law says you have no net charge. If you have a bounded space, then of course you can have a net charge with a corresponding electric field at the boundary. In gravity, things are more subtle, but basically the idea is the same. If you, say, freeze the intrinsic geometry of the boundary, then that's what you're freezing. You're not freezing basically the radial momentum corresponding to that, very heuristically the radial derivative of the metric there. And that's the thing that fluctuates. And that's the thing that plays the role of an energy. And there is an official definition of that energy, going back to York or Brown and York or in some combination, which is kind of what you'd naively think. It's this formula, the variation of the on-shell action with respect to this boundary metric, which is basically the extrinsic curvature of the boundary. Okay. Now, there are subtleties. There's a lot of other interesting boundary conditions, especially to think about in 4 dimensions where you fix some other combination of things. We kind of have in mind a microcanonical description, or again, keeping track of the energy levels of the system. Wait, I guess I went back rather than forward. Okay, so one really interesting thing about this setup, and this is again where different groups are coming together, is that these authors, Draper, Farkas, Banahashimi, Jacobson, et al., found the following. So people had been confused in the global de Sitter about the first law appearing to take a strange sign, the opposite sign. So they didn't have this Brown-York energy notion, so there's the Hamiltonian constraint says that this combination is 0, and if you interpret the matter energy in the system as the energy that's supposed to be there in the first law, well, it's a true fact that this sums to 0. However, if you consider the Brown-York energy as the notion of energy that's relevant, then you get the sign of the first law being the normal thing. And this is just what you would also get if you consider the system of a black hole and you have matter outside the black hole. You have energy that's contained in the black hole, energy that's contained in the matter outside the black hole. Yeah, please.
Where's the boundary right now? Is it at fixed r in static coordinates?
It's not described in, so let me describe it covariantly. It has a fixed circumference, fixed proper circumference.
And the observer is on the observer is looking out at the boundary.
Okay, so let me.
So they're in the static patch.
Yeah, so this picture is maybe too microscopic inadvertently. Sorry, I can draw it on the board, but people can't see. Is this visible or is it not? I have bigger pictures of it. So there's some spectrum of states, among which I think the dressing of your favorite band of energies, if I may speak for you, is the cosmic horizon patch, where in this picture the boundary would be where I've drawn it. So it's a cylinder, a flat cylinder, and we fill in toward the cosmic horizon. Since we fixed the proper circumference of the cylinder, we are not allowed to fix actually which direction we fill it in, right? The extrinsic curvature can be whatever it wants, so it can fill in that way. That's this sort of state can fill in the other way.
Is that the initial boundary diffeomorphically invariant?
The statement that you have the correct intrinsic geometry is certainly diffeomorphism invariant. Okay. That's why I like to respond not in terms of some coordinate system, but in terms of the proper geometry of the boundary. Okay, so now, what do we want to do to obtain this thing I advertised, where we are going to start with ADS-CFT and get to this de Sitter construction? So years ago, with Mika, who's I think here somewhere, and Ofer and others, people realized that multi-trace deformations of ADS-CFT are a thing, and that they change boundary conditions. Okay, so what we're looking for is some sort of multi-trace deformation that is going to change the boundary conditions in the way we like. And at the level of the gravitational description, the effective semi-classical theory on the gravity side, one can work that out. There's a beautiful paper of Tom et al. Doing that. They also looked at things in arbitrary dimensions. But for us, we'll mostly stick to 3 dimensions with gravity plus matter. Okay, so just in gravity variables, which would correspond to a putative large C or large N limit of some system that we're going to propose to define at finite C, it's a very nice analysis to see what it is that you want to do specifically. So you can organize that, as was really pioneered by these authors, is to process the Einstein equations, like the radial Hamiltonian constraint, rewrite it in terms of this Brown-York energy that I defined earlier, whereupon you get a formula for the trace of that Brown-York energy and some stuff on the right-hand side. So if you imagine a deformation that depends only on one dimensional parameter lambda, then this trace integrated can be identified with the way you want to vary the action. On the right-hand side, we have a particular quadratic combination of the stress energy tensor, which is the famous TT bar combination. Shouldn't be called TT bar, but that's that. And we have, for matter fields, some other stuff, like basically the radial momentum for the matter fields, and some stuff that depends on the Lagrangian, including the potential energy for it. So, of course, there's a lot of matter, and we'll be interested in just matter that's hanging around, and also an uplift sector from ADS to DS. Something we have bothered to model from the top down in 2 ways, by the way, this again being a string theory meeting. Like 15 years ago, Dong et al. Uplifted the D1, D5 theory, and recently DeLuca et al. Uplifted the M2 brane theory. Okay, so we have that in mind. The next thing I should say is that another of the Einstein equations, when we pick a good boundary condition for the matter field, gives us stress energy conservation. So that's what we want. We're interested in defining a bounded system, boxed-in system. No need necessarily to source it from outside. Just think of such a system and its spectrum. Okay, so we have a conserved stress energy. We have a statement about how we need to define the theory. Okay, in the map, the radial momentum, as I've said a few times, is the thing that fluctuates. So we identify that with the operator. There's some dictionary, which is more or less the thing you're used to in ADS3 CFT2, plus a map from kind of boundary-friendly to gravity-friendly variables. This L sub c will be the proper size of the cylinder that we discussed a moment ago. And so the trace relation I mentioned is the thing that tells us how to deform the action or the log of the partition function, if you think about it that way, which is this, formula. And you see, double trace in T, the nice TT bar operator, double trace in these operators O, which are the things that are more ugly to define. And as I said, we'll have an uplift sector for matter and other matter. Okay, so the thing that, yes, please. Yeah, sorry, thank you. Whoops, I did not want to end. Okay, sorry. Now, we are going back in time. Just uplift, that's our notation for uplift sector. Yeah, sorry. But thank you for the question. Okay. So as I'll review shortly, TT bar has very beautiful properties, OO not so much. There's a core of this theory, which is just TT bar, plus a constant you can add that doesn't ruin the solvability of it. So this is the developments over the last few years, starting with Grabenko et al., following up on the whole TT bar formalism. So there's a core of it that's that. There's a part of it that has to do with the matter fields, where we must define this composite operator so as to match to Tom et al.'s results at large N. And that includes the uplift sector. So the way we're going to do it is quite brute force as far as the matter goes. We are going to use what we know about TT bar to do a tiny bit of just pure TT bar to begin with, at a scale by an amount that's a regulator at some fixed amount, but can be arbitrarily small. So this does some damage to the locality properties of the theory to just cut it off at some energy scale, but we can make that so high that in ADS-CFT it just affects things that are at energies that are sensitive to quantum gravity anyway. So we're using the news of the past, whatever it is, 5 or 6 years, that we know finally how to regulate, at least a way, to regulate ADS-CFT where we know what it is on both sides. That's this. Once we have that, we have a finite theory, at which point we can start, we can make explicit the both the regularization and the subtraction to define this operator to match the results of GR. So that's the entire plan of action. And it's quite brute force. We're just going to force it to match. But we know, that's a well-defined algorithm if you like to do that. Ronak.
So when you think about TT bar as a regulator, you mentioned it's a regulator, you know what to do, like where you know.
Yeah.
But of course, since TT bar does not give you the Hamiltonian Wheeler-DeWitt equation, that's the right Hamiltonian constraint for the bulk, what is the advantage over just tracking up the spectrum by hand?
Well, it's a way to cut off the spectrum where you know that it's obtained by the nonlinear application of TT bar on the one hand. On the other hand, for just gravity, it's consistent with having cut it off radially. Okay, that's. But I agree with you. There might be in 4 dimensions. You might think about just not even. I'm going to say 2 things about 4 dimensions. One of them is in the spirit of what you asked. Okay. Anyway, so what we're going to propose is a 4-step process where we do this regulator thing to begin with. Then we start adding TT bar, which is pretty, OO, which is ugly. Then we do the uplift to de Sitter, and then we start adding this lambda 2 addendum to TT bar plus OO, because that's where we got for after the uplift. That's the thing that matches the quasi-local energies and the, as we'll see, the entropy for the de Sitter after the uplift. So it's a 4-part trajectory. The main point of this, so I'm getting ahead a little bit, but in the solvable TT bar plus lambda 2 world, we can produce for you the expression analytically for the energy spectrum. I will not achieve that with matter. So that's why we refer to this thing with matter as an algorithm. I can tell you what to do at the next step, but I don't know how to resum it. Sort of like gradient descent or something. You tell you what to do at the next step, does something, sometimes it has good convergence properties, whatever. So that's what we'll do. But the point of that, I mean, there is more structure to it that I'll try to mention. That's quite interesting when you add matter. But the point of that is just, at the very least, to establish that this solvable core of the theory, which already captures the entropy and already captures the radial geometry, that does embed into a complete theory at finite C, which matches what it's supposed to. Okay, so that's, we're not going to get an analytic solution for the energy levels of this complete theory. We're just going to give an algorithm to establish that it exists. Okay, now the bulk physics is quite interesting and generally, of course, time dependent and all that. So I may get a chance to say a little bit about it. Okay, whoops. Okay, so for those who haven't been in this world, let me first explain the nice solvable part of the theory and then get to a little more about the matter part. So the idea indeed is to, even with this pure TT bar, is to define the theory as some sort of differential equation, some sort of algorithm. And here it is. I've already added this lambda 2, which we understood with Victor and Gonzalo to retain the solvability properties. There's also interesting like square root TT bar that Christian and others have found that does that, where this is the equation. And the boundary conditions on this equation include that we are going to start with a seed CFT. So when we first begin this deformation, we turn off this term and we go back as lambda goes to 0 to a CFT with its known spectrum, or the properties of the spectrum are known well enough for our purposes. At this level, we do TT bar for a while, and then we start adding the lambda 2 to get to a theory whose entropy is dominated by the cosmic horizon patch I just mentioned. So this is the sort of theory. As people generally, I think, are aware, this composite operator TT bar is very simple and special. It factorizes up to total derivatives, which disappear in the deformation equation. That leads to a differential equation for, if you like, the interaction Hamiltonian. And if you then plug in the expression for the pressure in simple situations, although this expression for the pressure does not hold with matter in general, you get a differential equation for the energy levels with the boundary condition I mentioned, which is solved, which is solvable. And I'll give you the solution in a moment. This equation is also a consequence in gravity variables of the Einstein equations. So the Brown-York energy I introduced earlier, I haven't written them here, but it's the same equation. So the Einstein equations imply the very same equation for the Brown-York notion of energy. Okay. It's the same thing that I cited Hartman et al. For, but just turning off the matter for the moment. Okay, so the general solution of this thing is here. There's a branch of the square root involved, and there's an integration constant, which we match to each of these segments of the trajectory, to the endpoints of those. At this point, I'm just going to say when we match, say, to the seed CFT spectrum, there's a negative energy that appears in there. And famously, although the CFT has an infinite spectrum, this theory has a finite real spectrum. Okay, and that's going to be important. Basically, the finiteness of the de Sitter entropy is a direct consequence of the finiteness of the real spectrum of the TT bar plus lambda 2 deformed theory. Okay, so I said this before because there were some questions, but the sign of the square root is not fixed in general. So once we get to the Sitter, you can fill in either direction, and that's a kind of normalizable excitation. So that's how both the cosmic horizon and the pole patch appear in the spectrum. Okay. So at the level of pure gravity, there's stuff like the cosmic horizon, and before we get to De Sitter, there's BTZ black hole horizons, and a lot of the discussion has centered on them. There are also these so-called boundary gravitons, which are fluctuations of the extrinsic curvature. And you can analyze these linearly, nonlinear, classically, at the quantum level. And we're actually going back to analyze a bit more of the classical nonlinear dynamics of them. But the thing to say at this level is that in beautiful work of the UCLA group, it has been shown that they are governed, not surprisingly, since I told you the Einstein equations map to the TT bar plus lambda 2 equations. They showed that these boundary gravitons are governed by a nonlinear Born-Infeld action, just like is the dressed action for a free boson, CFT in general. As a result, they fit into the square root dressed energy spectrum, which at the quantum level is finite. Okay, so there's probably more to say about that, but this is the kind of bottom line for these modes. Okay, I keep saying this because I'm tempted to do some sort of check of what they would, what the dynamics of these things would be if we entertain them in 4 dimensions in the real universe. Because for all we know, there could be some boundary somewhere. In that scenario, we're an observer quite far away from the boundary. We're not sitting on it, obviously, that we can exclude. And what I'm saying about that here is that this kind of dynamics in 4 dimensions would be important for such a question. Yes? What happens to the action? I mean, I would have to go back and think about it again in the path integral language. But
I think that action is chosen by the minus sign.
I mean, let me just stick for now to the Hamiltonian description, and I'm allowed to include in my Hamiltonian these 2 sectors. Okay, and I'm saying that's the right thing to do one way to see that that's the right thing to do to match to gravity is that in gravity you're fixing the intrinsic geometry of the boundary and you have no right to fix the extrinsic curvature. You'll probably have something in mind about the path integral formalism, which I'll get back to afterwards, if that's all right. But yeah, it's probably related to the branch of the square root of the dressed action, the dressed classical action as well. But I usually think in this language. So anyway, so this is the kind of summary of this pure gravity sector, where you start from ADS-CFT, which has an infinite spectrum. You deform in the way I summarized. By the way, when we start this TT bar plus lambda 2 deformation, what's going on in gravity variables is that this boundary, which started out, say in this level of states of around delta equals C over 6, started out, at the boundary, it shrunk in its proper size, and eventually is sitting at the horizon of that black hole, at which point you can't tell it's DS or ADS with a black hole, and that's why we can do this lambda 2 addition at that point without losing continuity. And so the upshot is some deformation that takes you from an infinite spectrum to a finite real spectrum in a calculable way. And I guess I said these things before, but indeed the finite de Sitter entropy is a direct consequence of the finite real spectrum of these TT bar-like theories. Okay, so let me start on the trajectory that we consider and propose to capture the matter. I more or less said this before, actually, but I'll say a little bit more about it. When we add a little bit of TT bar to begin with, we have the dressed energy formula, which cuts off the real spectrum, at which point we can at least define operators without any ambiguity. I mean, we have a lot of freedom to define the operators as we wish. Okay, so the problem with an operator like OO is it, if you try to bring 2 points together, there's a piece that looks like 1 over c times, O at x, O at y, looks like 1 over c times 1 over x minus y to the appropriate power. So it's 0 times infinity, and at large c, if you take c to 0 to infinity first, okay, you don't see that term, but we see that term, and so we have to indeed subtract such things. Okay, I already said this, but remember that even for light, that is, even for massless degrees of freedom, it takes an infinite energy to get to the ADS boundary. So if we just put that arbitrarily high, we are sacrificing for quantum gravity level states. Okay, so next thing I'm going to do is to just argue that we can do this by brute force if we had to. So there's some nice structure to it where likely all you really have to do is at each step subtract a few terms, like I just kind of indicated. However, if I just had to tell you I'm going to match to Tom's calculations at the next step, I have enough degrees of freedom to do it. So I have these universal states, meaning the ones that are visible in gravity, then excited by matter, so we can compute expectation values of this sort. And you know, they in gravity can't get with distances below the Newton constant and be under control. We also can't go to arbitrarily late time scales and be under control. And so the number of these things really is finite and smaller than the capacity we have to just tune our heads off to match them. Okay, so now this is, you know, I want to stress how ugly and brute force this is, but it's meant to show that we can do it. And I will say a little more interesting things about the structure of these things. Okay, so that's the algorithm in general. Perfect, I think perfect. In this paper, we did a lot of work on the solution space of these theories. We had fun with taking some such gravity background, cosmic horizon patch, BTZ, outside the horizon pole patch, vacuum ADS, exciting standing waves of matter, and looking at the structure of these solutions. We can do that at the leading non-trivial order. And in this context, what that means is the following. So the matter feels like it lives on that geometry, but to get the energy, you have to do the order G Newton back reaction on the metric or on the extrinsic curvature because of the fact that there's this 1 over G Newton in the stress tensor expression. Okay, so you can do that. It's a good initial boundary value problem, and one thing we find that is very nice, it seems to be nice anyway, is that I mentioned there's this square root in the energy formula. When we excite matter in the way I just described, the effects of the matter end up multiplying that square root, which is curious and convenient because it's saying at this level that's not affecting the reality of the spectrum. I've already confessed, not surprisingly, that this plus OO uplift, et cetera, stuff is certainly not exactly solvable the way that the very type 1 fun TT bar plus lambda 2 is. However, one can study effects on both sides. And we do have a calculation of the dressed energy in assuming situations where there's an equation of state, which we can do on both sides. In general, as I stressed earlier, the expression for the pressure is not as simple as it is in the normal TT bar stuff. So, and there's these other matter terms, so we don't have a general solution. Okay, so so again, we have this 4-part trajectory. I've kind of already said this, I guess, but TT bar to regulate, then to form. It's 3 steps where we first go to this point where in the pure gravity theory we could start turning on the lambda 2. At that point, we then separately do the uplift. So that means we have some scalar that interpolates between the ADS solution and the DS solution. And we pull its boundary condition, which is a source in the boundary theory description, continuously up from its ADS value to its DS value, and the solution space continuously adjusts to that. And then we keep going with the TT bar plus lambda 2 plus OO. So I already kind of said that. Yeah, in the gravity language, we're changing the size of the bounding cylinder to the corresponding point where we need to do the uplift. And then we keep going and reducing the bounding cylinder with the uplift having been done. And everything is, yeah, okay. So here's the algorithm. Enjoy or don't enjoy it, depending on your taste. But this is really how we think about it. And again, even though this is kind of, I keep stressing, kind of a brute force tuning procedure, one point of it really is that it validates the nice solvable core of the theory, which we already had presented. One thing I want to note is that, we want to reconstruct the bulk. We want to understand how that works. But, let's face it, nobody needs holographers to do effective field theory. This comes up in, cosmology meetings where, theoretical cosmologists would love it if somehow it was, needed for them. Of course, it's not that effective field theory calculations are our job as when we think about quantum gravity. They're kind of a test for us, but they're not the point, right? So quantum gravity here is being invoked for what it is good for. For example, the microstates, the fine structure microstates is a job for quantum gravity. It's not accessible in EFT. So I'm not going to apologize. I've been apologizing all along, but I'm not going to apologize too much that we're just tuning to the effective field theory plus GR and letting this theory fill in the rest, the stuff that is that one does need quantum gravity for. Okay, I didn't really describe too much about the whole spectrum, but we have the matter excitations. There's also landscapey states that actually interpolate between the ADS and DS stuff. Of course, there are many other interesting approaches going on for de Sitter holography. Maybe an incomplete list is here, and it's a really vibrant and active area of research these days. By the way, there's a sequence of meetings that people keep organically organizing, and if anybody is interested in getting connected to that, you can do that. String theory, we have uplifts. Internally, when you get to this point where the horizon is, the boundary is skirting the horizon, it's, in some ensemble, at least, it's super high temperature. It can't help but mix between the very different internal states. And as I mentioned earlier, there's a really interesting question in string theory. Is the short scale boundary feature UV complete or not? So I want to advertise that and also advertise the Cambridge group making progress on that. Okay, this is, I don't know if this is a bold statement or not, but I want to make an analogy between the D1, D5 calculation where you use supersymmetry to control the state count and the TT bar type theories, which is not supersymmetry, but is integrability of the deformation to control the state count in a similar way. And in this first case, it embedded into ADS CFT here. We're saying it embeds into this plus OO theory. With Ronak and others, we are looking at whether we can use the same kind of idea to also formulate DS CFT. So how would that go? Well, instead of pulling the boundary out toward the pole, we boldly cross the horizon after the uplift and pull it up. The address classical action should go from a CFT to this non-CFT deformed theory, but by the time you get up here, it should be now a CFT with weird non-unitary properties. And okay, we're finding that at some level, although we have a lot of work to do to really interpret it. But this is something that's in play right now. Okay, 4D would be great. Yeah, I've been talking with Dio and company, and hopefully George also, about the situation in 4D. And I'm very tempted to think about actual phenomenological constraints on that, if indeed there's a bottom-up prescription at least that makes sense with some set of boundary conditions. If we're looking at sources in such a universe, and we're over here, there'd be light from them, there'd be reflected light from them, it'd be sort of like lensing, except it's a different, very different phenomenology. It's something that things can bounce off. There'd be sort of chaotic dynamics where there wouldn't otherwise. So I think that would be a fun problem. So let me leave you with that, and here's the recap.
Okay, we have questions. Let me remind you there are microphones over there, and somebody should perhaps grab them and pass them around. Okay, questions.
I guess I have a really basic question. I mean, before you added the matter, you were talking about this transition starting with ADS going to the horizon and coming back by adding lambda and stuff.
Yeah.
And then you added the matter, and you showed this potential for a scalar with an ADS and a de Sitter minimum.
Right.
So are you now replacing but you seem to have both now. You seem to have
No, good question. Thanks for the question. Let me just make sure it's clear. The uplift to the de Sitter minimum is indeed playing the role of lambda 2. Once you're at that point, you can then describe the situation as you have lambda 2 in place. It's part of this general formula that I wrote for trace T equals stuff. So it's not that you're double counting that. I'm sorry if the notation wasn't clear, but it's...
But you don't need lambda 2 if you...
The positive CC is playing the role of lambda 2, so it's in there.
Yeah.
But yeah, thanks for the question. George.
Just one comment. In higher dimensions, we don't even know what boundary conditions we should consider for the dynamical problem. For the elliptic problem, we have now a large class of boundary conditions, at least to a well-posed problem. But for the time evolution problem, we don't even know which boundary conditions we should choose.
I appreciate that, and I want to catch up with you on that. I did speak just last week to Dio and Damien about it. You guys have sort of similar papers, I guess. And I think they were saying, well, we should talk later, but with the conformal boundary condition, with a CC in place in the bulk, they were saying the possible instabilities were milder in some way, but maybe I don't think
this is an issue with the instabilities. This is an issue about local uniqueness. You cannot predict that if you start with some initial data and some right boundary conditions that you can predict the bulk uniquely.
No, I totally agree with that. However, let me stress, and I would love for you to reply to this if I'm missing something, but for this problem, I am not demanding to be able to have whatever boundary intrinsic geometry I want. I'm saying if a special case is good, we're fine.
But what I'm trying to tell you is that there's no special case that is good.
Is that right?
Because it's as you pointed out, it's a UV problem. So it's, if you go to very, very, very short length scales, it's like having a flat boundary. Whatever is the boundary that you choose is like having a flat boundary. And then you run into problems with uniqueness.
Okay, so
but it's a UV problem. You're absolutely right. It could be that, it could be that it's cured by string theory or something like that.
Okay,
but it's a big jump.
These are great comments. I'm totally appreciate that, and also that it's a job for string theory, which is, I don't know if it's a bug or a feature, but it's the right methodology that we need. I do want to catch up with you because I thought that Dio and Damien were finding that for some cases of Dirichlet, even though you would think there'd be this corner issue locally, that it was regulated by the curvature of the boundary, and you disagree. I don't want to put words in their mouth, so this is recorded, but I definitely want to catch up on...
You can record this, I disagree.
So I didn't hear that, but this is a live subject, as I tried to, and these are really nice papers. Could boundary conditions like involve matter in some way, stabilizing things or stuff like that?
Sure, it could, but
yeah. So it's a world of questions, and you have a new family, but there could be other families. And
the new family is for the elliptic problem. So
we should set this aside. Let's do one more question while Samir sets up for the next talk. Mukund,
Yeah, I was just trying to figure out what makes de Sitter entropy finite in this construction. Just the TT bar deformation which truncates the spectrum, or something else? Because at some point you also had finite C and some comments about type 1 algebras.
Yeah.
Because you're still in a semi-classical regime where C is large.
We are okay. I want to be super clear. This is a finite C theory that we are constructing. I spent some time in the talk reviewing, Tom and company's beautiful work in the large C limit, which is telling us the thing we need to match, the kind of double trace operators we need to add at every step. But then we're working at finite C. and with this regulator in place so that we can match that. The finiteness of the de Sitter spectrum being the right thing for the de Sitter entropy is more than just the fact that we regulated the system at first. Instead, as you continue to evolve on this trajectory, the dimension of the real spectrum reduces. And once you're at this point where you're bounding the horizon, it's at the lowest it ever goes, which is the refined entropy of that horizon. It has the -3 log as well, so Ashok's thing matches to Dio's thing, and that had to be true in our theory, but that's where the finiteness comes from, and it's preserved then as you continue with the lambda 2. But yeah, this is all in 3 dimensions where the boundary conditions aren't as subtle. So,
Thanks.
thank you.
Okay, let's thank Eva again.